I will continue with
It's 8 o'clock.
with the parallel plate waveguide that has the multiple dielectric layers. I will do one of those, and then I will talk about the circuit representations of the other configurations. You can do all kinds of different configurations, but pay attention to one that I will do for the parallel plate with the multiple dielectrics, because that will be useful for homework and so forth. And then today, one other thing that I wanted to mention, and I will share my screen right now, just 1 second. I will share the screen, home, to this, share, okay, start. Just to two things that I wanted to tell you. First of all, about making it easier for you to find the hours for the office hours, when office hours take place, and the links and so forth for the office hours. I went into on the main page. That's where I said everything, all the information is. And if, for example, you start with this week, which is week 7, and we are doing module 6. Do you see here on where I say, like, today's Wednesday, and I have the two sets of materials that will be useful for today. One is what I will finish from Monday's lecture, and the other is one that I'm going to start with, and I will continue on that. But below it, it says problem solving session from 4:30 to 6:30 p.m. today, and I have the Zoom link next to it. And I will do that for all of the office hours, also for Sunday, because a lot of students are confused, maybe because on Zoom, if you go under Zoom, it shows all of this. So under Zoom, use it only for the lectures. It's one only Zoom link for the lectures every morning. And then these ones, because they change, the numbers change. For example, I cannot do one weekly that has different hours, so they change. And so also, if you go to the next week, I will do the same. So every day you're going to see the office hours, the Zoom link to connect, and the problem solving session. And from the problem solving session, I will always upload my notes and the Zoom video. So this morning after the class, I will finish up the two videos for Monday, the video for Monday rather. And then by Friday, we'll have uploaded all the videos. So that is one thing. The other thing we discussed, because we start jumping from one section to another in the textbook, I went from the beginning of this class. I'm not going to go all the way up, but you will notice, like here, week 6, electrostatic fields, my notes always. And then from textbook, I have put the specific sections that we have covered from different chapters. So for example, here you're going to see from chapter 4. This is part of chapter 4. Previous week from the early sections of chapter 4. So this is going to give you some guidance which sections of the textbook we have covered. Okay, so everything, all is here. Don't look for anything else, anywhere else. Don't get confused. You're going to always follow this page to help you. All right. I know that online is confusing, is way too much information that we would normally not have to put online like this, or at least the links, for example. If everything is face to face, then we will not have to worry about those. But in any case, this is what it is now. And I want to help you so you don't get confused with all of this information. You don't know where to find it. It's all in one place. Any questions about those? Okay. The second thing, I put a new survey. I told you that I was going to put a new survey. And if you go under quizzes, that's where you find the surveys. It is under quizzes. And you see the second survey. It says your thoughts about the class and suggestions for improvements. And you're going to get 55 points from this, because for every question there will be 5. So I'm asking you very specific questions. Please finish that by Sunday, because it's going to give me some information about what are the things that you would like to see, how things work for you, and so forth. And please provide suggestions. If something you feel needs to change, it would be very helpful. So instead of telling me, well, that is not working for me, to also make a suggestion of what you think could improve your learning. Because otherwise I will know that there is a problem, but if you don't provide some suggestions, whatever I do may not necessarily be helpful to you, all right? I will make a change, but I need to be guided in those changes that I will make. Any questions about those before we start with the lecture today? Okay. So let me see, I'm going to our notes here. All right. You will find this is where we are going to start, but I would like to finish with what we started last time. So I'm going to go back here, and we are in week 7. And last time we talked about one thing, keep it in mind, because I'm going to come back to it. Look at this picture here that I want you to remain in your brain as much as, you know, anything else important. That whenever you have a conductor, because there cannot be an electric field on the surface of the conductor, all the fields in the conductor and on the surface, all the fields which are inside the conductor, tangential to the surface, rather, to be more appropriate, more accurate, have to go to 0. Because by definition, the way we define perfect conductors is that there is no charge inside a perfect conductor. All the charges, if any, are on the surface. If there is no movement of charges inside the conductor, so there is 0 movement of charges inside the conductor, so there cannot be any electric field inside the conductor or even parallel to the surface of the conductor and inside, obviously. And that forces the electric field, when it comes from the outside towards the conductor, to end on the conductor in a perpendicular manner, like you see here. This applies to electric fields, and it applies to electric flux densities, because the electric flux density and the electric field are related through a scalar. And the relationship here for that, as you know, is that D equals epsilon E, where epsilon, just to remind you, is epsilon R, epsilon naught, and for air, epsilon R equals 1. Okay? That's where what we remember. Now, we have talked about this problem and we've solved it. So I'm not gonna go there. And here that shows some ideas about parallel plate capacitors. So some people asked, okay, we need to know the parallel plate capacitor, obviously, because we try to develop a capacitor for a specific capacitance. Why capacitors are important? Because they store charge, and then they can release it whenever we want it to be released. Very important functions, obviously. So obviously we need to know how to design those capacitors for a particular capacitance. At the same time, capacitance also is important to know. Why is that? Because if you happen to have 2 lines that cross each other, And the lines are not supposed to interact because they are just lines on a printed circuit board, because a printed circuit board has multiple layers. Here that shows like a possible circuit, all right? I mean, how it is fabricated. You may have devices at usually the active devices at the lower level here. So these will be transistors. And then on top of these multiple dielectric layers for different what we call interconnects, like the green one. And there are interconnects that go in different ways. You remember when I showed them, some they go parallel, some they cross like vertically, some they cross at other angles and so forth. All of this. And if there are 1,000,000 transistors, there are 10 million interconnects. Now you need to remember 1,000,000 is nothing, because in one of your devices, your cell phones, you know how many transistors there are? I may have said that, but who can tell me how many transistors there are in here? Any guesses? Somebody said 7 million. Anybody else? Any other takes?
Several billion.
Is it a billion?
It is 1 billion today and more. 1 billion. 1B. You know how many billion lines there are in there? Now it is not, you cannot understand, how it is even possible, because 1 billion is like when my kids were going to school, the name for the billion was Google. Now Google is a name for something else, but at the time, if you would ask my daughter like 30 some years ago, what is 1,000? She would say Google. All right, that's how far it is. People cannot even have the sense of what it means, 1 billion. If there are 1 billion transistors, you have at least 100 billion interconnects. Now, nobody is going to design this one by one. Usually it is designed like a brick. All right. So for example, when you build a brick building, how many bricks you have in there if it's a complex building like on the East Coast? Millions. All right. Nobody's going to design every brick separately. No. Otherwise, we will never have brick buildings. You design one brick, and then you design how you put them together. And that's it. And sometimes you put the whole wall together, and then you move the walls. That's how they do the circuit design. However, when they design the one brick, and that one brick, for example, and one block that we call it for circuits, for a cell phone, may have like 1,000 transistors, all right, or 100 transistors, even if you go to smaller blocks, because the way they go is a small block, many small blocks make a bigger one. And a big block, many small big blocks make even a larger one, and so forth. So when they start the fundamental design of the smaller blocks, they make sure that the lines, they may be there, lots of them, but they are at a distance. You remember we talked about crosstalk. Okay, we talked about all of this crosstalk, but the fundamental thing is it's one way to talk about this like that, descriptive, in a descriptive way. And it's another way of trying to calculate it. How would you calculate crosstalk? We talk about it, but how would I ask you now? I can ask one of you, say, okay, I have these two lines. I have one line coming like this here. This is one interconnect. And this interconnect is on one layer. All right. And then I have another layer on top of this, or maybe two layers, different dielectrics. And then there is another interconnect, but this one goes perpendicularly. So I can see it along the long, on the side, for example. This interconnect, I can see it on the side like this. All right, two. So practically one comes like this, the red one, and the purple one comes like this, if you look at them from the top. So they overlap, There is an overlap here, like this. That's where they intersect. Okay, so there is crosstalk because of that. How do you calculate the crosstalk? What do you suspect I will tell you next? In the form of what in circuits? What is that? What is this symbol? That it's a capacitance, all right? You see that? So how do I calculate crosstalk? I look at this area and I say in this area, maybe I need to use a different color. So I look at this area here and I say it is this area where they come the closest to each other, like here. So I'm going to calculate the capacitance between these. If I calculate the capacitance between these two lines, then practically when we start developing the circuit representation and when we go to transmission lines, remind me, you're going to see that. I'm going to come and make a reference to this, because then the way we are going to show it, we are going to show one transmission line later looking like this, like two wires. We are going to symbolically show it like that. Another transmission line is going to be like this. And usually those, they show like it will come the other way. All right. So symbolically, we are going to show it like that. And in between the two is going to be a capacitance. And that capacitance is the crosstalk. And how do we calculate the capacitance for this one here? How do we calculate this capacitance? From here, from this one. So now you know why this is so important, not because I'm gonna give you a mathematical exercise and twist your brains a little bit, but because this is real. We use it real time, very important in circuit design. Without knowing this, I think you cannot start any circuit design. All right, so everything starts simple and then we built up. That's what you need to remember. That's why we went to like at least 1 billion of transistors here and then maybe 100 billion lines. There is no even computer who can do 100 billion interconnects and design something that has such a complex function. Unless you start with simple things and then you abstract up. So something that looks as complex as this one that I have now put around here, this line, at the end, you represent it by one capacitance. At the end, this whole mess here is going to be all of these. For me, is going to be one capacitance. That's it. And here it shows how we will calculate it. All right. So for you, I will remove this. And then just here, I wanted to bring your attention to something that is important to remember. Okay, so I will remove that because I need to make it a little bigger for you. That is not going to help you. All right. Now, what I will do here is the following. First of all, I will write two things. This is the capacitor we write. This is two lines. The two lines I made reference to, that they go over like this. Remember that this is nothing else but two lines on different substrates. One line is like this. That's one line on one substrate. And the other line is like this. Goes like that. And here it's how it goes. One line here, the red one has, let's assume that they are identical, but they just cross. W here, the other has W here. Okay. The other has W here. So this area here is A. All right, and the two lines are printed on two separate dielectrics, like you see here. So the green line is, to just give you an idea, is down here, goes like that, and then extends. And then over it, you have two dielectrics. One is this one, another is this one, two different dielectrics. And the red line comes vertically like this, perpendicularly rather. And then so it comes out of the paper. So this one probably is going to go like that. All right. So, and here you have two different dielectrics. One is this one, and the other is this one. All right. So this is the picture here that we are trying to study. These are the two interconnects, and we would like to find the crosstalk. So crosstalk in here, so practically say find the crosstalk between the two interconnects. Okay. Then how I'm going to start. Obviously, when I say find crosstalk, what I mean here, I mean find capacitance. Find capacitance between the two lines. Now, obviously, the capacitance is going to be dominated by the area of the two lines where they come the closest to each other. All right, because obviously if one line carries charges and the other line carries charges that go the other way, obviously there will be electric fields everywhere. However, the electric field will be strongest in the area where they are the closest. And the area where they are the closest is this one, area A. So what I do, I will take this picture. And what am I writing here? I'm writing the two boundary conditions on the interface. So first of all, I will write all the boundary conditions which are important. So what are the boundary conditions here? Boundary conditions. And the word says it conditions of the fields on the boundaries. First of all, the tangential component, and I will write it here. So number one, tangential electric field on the conductors is 0, okay? So on the top and bottom conductors, the E tangential on up and, so if this is conductor 1 and this is conductor 2, on here, 1, 2 is 0. So this is one condition. What is the other condition? At the interface, so we have boundaries on the upper conductor or the lower conductor and at the interface. These are our three boundaries, all right? So now we set the condition on the upper boundaries, the upper conductor, lower conductor. The other conditions we have is at the dielectric interface. Dielectric interface. What happens there? According to what we discussed last time, the normal components, and I will write it here. So the boundary conditions there say that normal D components are continuous through the interface. Which means if The upper dielectric is number 1, and the lower dielectric is number 2, as I have shown here. What do we have? That dN1 equals dN2. Okay, and of course, what else we know is that the tangential electric fields there, E tangential 1 should be equal to E tangential 2. All right. Now, what else do we know? We know that all the electric field lines have to be perpendicular to the metal, all right? So practically, because of the first condition, all E and D are perpendicular to conductors, which means that for a short distance like that, there is no way you can have anywhere a tangential component of the electric field. So all of the field lines look like here. They are all perpendicular to the conductors, which makes the number 1 to be correct. The other thing are the flux lines, flux, not the electric field, but the flux lines, which are perpendicular to the interface, are continuous. That's why when I show the red lines here, these lines that I show, here, these ones are perpendicular and they are continuous. You see them? I saw them like straight lines without any interruption. Okay, what else? So these are the boundary conditions. What else do we know? So far, we have satisfied these conditions, all right? On the picture and in our minds, that's what it is. We are developing now the solution as we proceed. Okay, now what else do we know? So now that we wrote here the conditions, and I will put them in one there. We write the additional things we know. And what we know additionally is that D1 is epsilon 1 E1, which means is epsilon 1 R, which is the relative dielectric constant, epsilon naught E1. And D2 equals epsilon 2 E2, epsilon 2 R, epsilon naught E2. And also we know that E1 has only the normal component to this. And for example, I can develop here a Cartesian coordinate system. This is Z. I can make this Y, and I can make this X if you like. And then what we know that this is E1 AZ, and E2 is E2 AZ. Okay, so these are all, now we put down everything that we know. What else is that we know here? We know that the upper conductor is at a potential VD. All right, so these are now other things. Upper conductor at potential V1 equals V sub D, because I put a battery. Lower conductor at potential V2 equals 0, because it's ground. All right, so also this we know.
I have a question.
Yes.
So why were we able to assume that the electric field is going in the Z direction?
Because that's the normal direction.
Okay.
And I introduced the Cartesian coordinate system.
Okay, I see. Thank you.
All right, you're welcome. And then what else do we now No. Okay, I think we have everything. So one more thing I will write here that we know. So let me put this here. We now know that E, we have defined it rather, is minus divergence of V. So we know now that the potential I'm talking about here, V1 and V2, is nothing else but this potential is the value of this potential V. So practically, V1 is the value of V at what Z if the thickness of the conductors, the separation between the conductors is H1 plus H2, all right? That's why I'm now in the coordinate system. So V1 is V at Z equals H1 plus H2, and V2 is nothing else but V at 0. So practically now, what is interesting here is by saying that we also have specified the potential values on the two conductors. Okay, so now we have this. What do we do from here as we discussed? From here, since we have only one component of the E field, we are going to have here that E, which is EZ along the Z direction, is going to be nothing else but minus theta V theta Z. Okay? And that's along the Z direction, according to the gradient. So then what do we do? So practically we know that E sub Z equals minus theta V theta Z. Now what do? We integrate EZ, this one, EZ, I said, I was supposed to say, dz, from the upper conductor to the lower, in fact, what do? We integrate from 1, which is lower, to 2, okay? From 1 to 2. All right, so this is equal to minus from 1, which is the upper conductor, to 2, because the electric field also goes down. Did you see that, how I have it? Because the positive charge is up there. And therefore the electric field is going to have, or the electric flux density will have that direction. Okay, and then I have, this is equal to minus theta V theta Z dz, which in fact that gives minus V when in the upper conductor Z equals H1 plus H2 minus V at Z equals 0. In fact, V2, what did I say? No, is the lower one, the opposite. I mixed up the ones and twos. So this is from V2, which is at Z equals 0, minus V at 1, which is at Z equals H1 plus H2. Okay, how much is V at 0? 0. How much is V according to this here? V at V is H1 plus H2 is V sub D. All right, so here we have that this integral is equal to VD. Okay, now let's see how that is. In this integral here, because we have this short distance and we have D that is continuous through the interface, because it's continuous and nothing changes, that means that D is constant. All right, so what we have here is that from 1 to 2 becomes the following. From conductor 1, which is the upper one, until, which is in fact when Z equals H1 plus H2 to Z equals what did I say, H2 of E in the upper, which is E1 dz plus from Z, which is H2 to 0 of V2 dz equals V sub D. And then I add here one more page. And what is E1? E1 is D1 over epsilon 1, and E2 is D2 over epsilon 2, but they are they're all along the Z direction. So I'll put them here. And D1Z equals to D2Z equals to D sub Z. And then I have from the above that this one here gives me, what do I have? Minus, in fact, because it's the electric field goes in the positive direction. Okay, so here you have to remember that when I do the fields, all right, so, and then I go down here, EZ, it goes down along the negative Z direction. So practically, I will have to take that negative into consideration when I remove the A sub Z's. So for to be accurate, all right, because I skipped a term, I skipped a step, which for me is not a problem because I will correct it later, but mathematically, I did something which was incorrect. Mathematically, E is along the negative Z direction. So I need to remember that that will be EAZ, whether it's 1 or 2, but the E1 and 2 will be negative values, all right? Because of the direction is negative, the way I have developed the Z, the coordinate system. So I need to remember that, and I will circle it with a red. So when we see a negative number coming down, we should not be surprised because the negative number is about to come. So from here we have, from the first integral, here, we are going to have minus H1 E1Z. And from the second one, we're going to have minus H2 E2Z equals V sub D. And from here, we're going to have minus of H1 epsilon 1 minus of H2 epsilon 2 D Z equals V sub D. Okay, now the negative signs are coming because of the negative direction of the electric field. And therefore, at this point, I will say I don't care about the negative direction of the electric field, so I will remove it. So now that I acknowledge that the negative sign is associated, negative is associated with direction, I will remove it because then I know what the direction is, and therefore I will say that H1 over E1 plus H2 over E2 dz equals V sub D, where the D is along this direction, and I put it like that so I remember it. All right, that's where I remove the negative sign. Okay, now what is D? That is what I need to bring your attention to. Let me go here, and I will take a teeny section of here on this interface, and I will show it up here. I will have, therefore, this interface. This is the conductor. And let's assume that this is, I took this small piece. And then all of this conductor here, what does it have? It has a uniform charge density, Q sub S, and it's a surface charge density, actually, because it has an area, even if we don't show it in 3D, all right? Okay, so this is the upper conductor. Then, in fact, don't need that, because it's kind of confusing. All right, then then let's stay there for a moment. Inside this area, the electric field is all zero. We said that. And of course, D is going to be all zero inside. So then we said that D in the outside is going to be perpendicular. So I'm going to show it here like this, not like that. Like this. Okay, let me show it like that, just to have space. Now, what I do, I take a small area here and I apply there because we know that at this point, we know that the divergence of D equals what? You remember that? That's Gauss's law. So if this is one point, and I go around that point and I create a small volume, which I call dV, then at that point, specifically the divergence of D equals Q sub S. Then what do I do from here? I integrate it around this small volume. And this one, I was supposed to do it here. Okay, and this one gives me the closed surface integral of D dot. Oh, excuse me, I forgot to put this other is around here. And that's gonna be dV Q sub S dV. So the volume, I do volume integral on both sides of Gauss's law. And therefore, this one becomes d dot ds. Now, if I only used a differential volume that goes only around one point, how much is the volume integral around this differential volume of Q sub S? Is it not Q sub S dV? Or rather Q sub S, because practically is Q sub S is the surface charge density. Assume that I got this teeny volume, which is around the point, a teeny volume, which is around this point, Q sub S, where only one Q sub S is here. So practically it will give me Q sub S. And now let me look at this volume. This volume is going to have, if I were to do it here in 3D, it will have 6 faces. It's going to have the upper face, the lower face, and all of the side faces. And to be able to find the surface contributions, that I need to find the inner product between D and the normal vector to the surface, because this is the surface direction. But D is only vertical. So on all side surfaces, the contribution of the integral is 0, because the electric field goes like this, or D goes vertical, and the surfaces, the side surfaces, have a direction perpendicular to that. All right. Then on upper surface, which is inside the conductor, also is 0, because there is no field inside the conductor. And the only contribution here comes from lower surface, which is right at the point. So that from there is going to be Q, all right? And it's going to be rather Q, because I'm around that exactly point. Excuse me, D, because I'm around that exactly point. So practically what I find here, and this is D vertical, all right? DZ, AZ. So practically what I found from this integral is that D at this point on the surface, so D sub n on surface of conductor equals Q sub S. This is a very important relationship. So whenever you need to remember it for every conductor, whenever you have a field on the surface of the conductor, the electric flux density, it's normal to the surface of the conductor and equal to the charge density at that point. You need to remember that this is across the board, we're going to use it exclusively. And so from there, if we put everything in this equation, say 1 and equation 2, practically from 1 and 2, you have the following, that, let me see, H1, epsilon 1. And now I will do it across the whole area, A. All right, so I can multiply everything by the area A, so you will see how it's going to go. But I will put D sub Z plus H2 over epsilon 2, and then I have Q sub S, and then equal to BD. So then what do? Then I multiply everything by A, so I have H1 over epsilon 1 plus H2 over epsilon 2. And then I multiply everything by the area, which is Q sub S A, and that gives me Q equals V sub D. So now I have the following, that V sub D is nothing else but Q, and then I have 1 over A, I multiplied already both sides, so then I have, let me see here, correct this, Q over A, H1 over epsilon 1 plus H2 over epsilon 2. And if I take this, all of this that I did, back to up this one, you will come exactly to what I have this one here. Now we define, so I did practically what we did in B, but I did it with a lot of detail. So from B, we found the same relationship as I did down here. You see that I finally found this relationship is the same, all right? This one. So this relationship is identical with what I have up here, this one. But I did it so you, at least once, we're not gonna keep doing this again, but once, because you can repeat the same thing with everything else. And then from there, we define the capacitance as the ratio of Q over V. V is V sub D in our case. And then what we find is that if the capacitance for one capacitor, one parallel plate capacitor with one dielectric is given by this, then with two dielectrics, one flat, with two dielectrics that lay one on top of each other like this, is going to be given like a capacitance which is in series. So this arrangement is equivalent to two capacitors in series. Now you can repeat the same, and I suggest you do as an exercise to practice to prove this one, that when the two dielectrics are one to the left and one to the right here, then the two again, you can prove that there will be a capacitance which comes as the sum. So like a parallel combination of two capacitors. All right, so you have that. And then eventually you can do all kind of other configurations. And I would like you to do these other configurations as an exercise, as practice. Okay, so you figure out how you do this and how you do that. Everything is identical with what I have here, which I'm going to load up to your notes so you can see that, but I would like you to do the other 3 examples as an exercise at home.
Professor?
Yes.
Earlier, whenever writing the dn over on surface
Yes.
equals QS, you said when the electric charge on a surface, or when you have an electric field on the surface of a conductor, the electric flux density is perpendicular to the surface. And then you said something else, but I didn't get that
And
last
it's
part.
equal to this. I said 2.
Oh, okay.
See, is equal to the charge density at that point.
Okay, thank you.
You're welcome. Any other questions? Yes.
Yes,
Professor.
Professor.
Yes.
Oh, sorry, go ahead.
Okay, thanks. So you, for the questions that you want us to solve ourselves, can you
Yes.
scroll down to the bottom?
Yes. That 1 and 2 and 3. So 1 is here.
Can we like take shortcuts?
Of course you can take
like-
shortcuts. Yes.
I mean, using the stuff we already proved, which is in parallel and in series, and
Yes.
then use them to
Yes.
prove.
But I would, of course you can do shortcuts, but before from now on, but I would like you for practice to prove these are the shortcuts that I've done. These are my shortcuts, you see? This is a shortcut. But what I would like you to do for practice is to prove it the way I did, like this, to feel comfortable doing this exercise, this one here that I have in front of you. I want you to solve this, not as extensively. I did this before extensively to make sure you understand every single reason I'm going through one step right after the other. So I want you to do this, and then I want you to do those because I may give you something. Now, I know you will know how to do the shortcuts, but if you don't know how to do the shortcut, then what if I give you something that looks like this? I may give you something like that in the exam that looks like this, with 1, 2, 3, 4 dielectrics. Or what have I given you for homework? What if I give you, let me see the homework, in fact, for a moment. Homework, where's homework here? I don't have 4. Do you remember homework 4? I have it in my other computer. So homework 4, where is here? If I can find it. Homework 4. There. Let me see. Homework. No. Yeah. Homework 4. No. 5 I meant. Do we have 4? Yes, here. Homework 5. Where's 5? Okay. Now look at this. Well, this is one coaxial, but look at that. Very similar like before, but in cylindrical coordinates. So I want you to practice what I've done for the parallel plate capacitor, because the same kind of idea you have to apply here. All right, to be able to solve your homework. Because I have 2 dielectrics here. I ask you to solve this, first of all, to help you. So you solve this, and you find the capacitance per unit length for this one. And then, and I should unit, I put an E at the end, just noticed. And then I put two dielectrics. But the process that you're gonna do exactly the same kind of process that we did with a parallel plate capacitor. All right? So yeah, eventually you can do for the parallel plate capacitor shortcut for you, but when you come here, I have not told you what kind of short you have. I want you to show, I want to see your derivations. Got it?
Gotcha. Thank you.
Perfect. Thank you.
Professor?
Yes.
Going back to that example that you just did, I got lost. I was trying to figure out how we get the units. So starting at the when you integrated the
The unit? Yes.
yeah, but no, right there.
Yeah.
At the double integral of the
Yes.
density with surface area. I got lost because I
The
can't
unit
see
is
how you
okay.
get how you integrate the density and then get out small charge at the density at the same time.
Practically, ideally, I would have here the following. I would have a dV here to be correct with my units. All right.
But that should just be a unit vector since it's just a normal surface, right?
So because that's a volume, but it's going to be exactly, it's going to be because it's a surface and because it's only on the surface. Practically, this is going to be Q sub S only ds. All right, because there is only on the surface, and this is Q in surface units, and this is surface, so this is Q.
Okay, and what are the units of that? That should be
Coulomb.
Charge per.
Yeah, Q sub S is coulombs per meter square, for example. Okay, the units of Q sub S will be coulombs per meter square, for example, or centimeter square. And this is gonna be meter square or centimeter square. And then, so eventually the product of the two is gonna give you coulombs. So yes, you're right that the units are not here, correct? But you need to remember this is these at one point. So on this, so the units here will be correct. I mean, the units on the left and the units on the right should come out to be right. Because
Okay.
this bend on that point is at a point, you remember? This bend is at a point, then the units between the two should be right.
Okay. Okay, thank you.
You're welcome. Any other questions?
Professor?
Yes.
When were you planning on posting these notes?
Now, before I do anything else, I will put them up right now. And in fact, usually I clean them up for some reason, but probably I should not do that here because it takes some time. I just need to clean them up. Let me see. Make them a little shorter so you can fit on one page here. There. And this one's a little shorter. No. And then this one a little shorter. Okay, do this. And then it's ready to go, I think. So I will send it to myself. There's a process here to be able to send it as a PDF file so you can see what I'm doing, how I'm working. So to myself. And I will take that and upload it. And I will do this right now.
Okay, thank you.
You're welcome. Any other questions? Okay. We'll see you on Wednesday. No exercise today. So you guys know. We are not going to have an exercise today. We'll give ourselves a break. Thank you.
It's 9 o'clock.